In this section, we introduce hypothesis testing. A hypothesis test is a procedure for testing a claim about a property. Some basic concepts for hypothesis testing are as follows. Identifying null and alternative hypothesis, calculating the test statistic, identifying critical values, how to identify the p-value, and how to state the conclusion of a hypothesis. More on the basic concepts of hypothesis testing. The null hypothesis, H sub 0, is a statement that has equality in it, as written here. The alternate hypothesis does not have equality in it and is denoted a few ways, as written here. When forming a claim, it is best not to use equality in the claim. An example. Example A has the claim in the form of the null hypothesis, which is P equals 0.20. This means that the alternate hypothesis is going to be P is not equal to 0.20. Example B states the claim in the form of the alternate hypothesis, which we write as P greater than 0.50. And the null hypothesis is P equals 0.50. Example C states the claim that standard deviation is less than 40 seconds, which is in the form of the alternate hypothesis, sigma less than 40 seconds. And so the null hypothesis is sigma equals 40 seconds. We need the test statistic to make a decision about the null hypothesis. The formulas are labeled here. Now let's do an example. Here the claim is less than 1/2 of adults have carbon monoxide detectors in the U.S. A survey of N equals 1005 said that 462 had carbon monoxide detectors. The claim is in the form of the alternate hypothesis, P less than 0.50. Null hypothesis is then P equals 0.50. Let's rewrite the test statistic formula for proportion. We do need p hat, which is our sample proportion. Evaluating this on the calculator. Rounding to 3 decimal places here, we get 0.460. Now we just plug our information in the formula to get the test statistic. And we get the test statistic being negative 2.54. We would use this to help make a decision on the null hypothesis. The critical region is a set of all values of the test statistic that cause us to reject the null hypothesis. The significance level, denoted alpha, is the probability that the test statistic will fall in the critical region when the null hypothesis is actually true. If the test statistic falls in the critical region, we reject the null hypothesis. A critical value is any value that separates the critical region from the values of the test statistic that do not lead to the rejection of the null hypothesis. Here is a diagram of what the right tail test looks like, where the critical region is on the right tail of the critical value. For a left-tailed test, the parameter is less than assumed value and the critical region is in the left tail of the critical value. A two-tailed test is where the parameter is not equal to assumed value and the critical region is split up into the right and left tails. An example. Example A is a two-tailed test, so critical region is split up between left and right tail. Finding the critical values, we use the inverse norm function on our calculator. In this example, here is what HO and HA look like for the two-tailed test. Example B, we have a left-tailed test. And critical region of 0.10, again, we find the critical value using the inverse norm function on the calculator. Here is what HO and HA look like for the left-tailed test. Example C, this is a right-tailed test with critical region being 0.01. Using inverse norm to find the critical value separating the critical region. Example D is a two-tailed test. So critical region is split up into two places. Again, using inverse norm to find the critical values. So the critical values are plus or minus 2.81. Now let's do an example finding the p-values. Example A, we're given a right-tailed test and test statistic of 2.50. To calculate the p-value, we hit second bars, then go to normal CDF and enter lower and the upper value. And we get 0.006 as our p-value. And notice that 0.006 is less than 0.05, our significance value. Example B, we have a two-tailed test and test statistic of negative 0.55. P-value for this case, we multiply normal CDF by 2. And we get 0.582 as the p-value, which notice is greater than our 0.05 significance. Example C is a left-tailed test, and test statistic is negative 2.95. Plugging into the calculator using the normal CDF function. Whoops, use normal PDF instead of normal CDF. Recalculating, we get p-value of 0.0016, which, notice, is less than 0.05. Example D, we have a two-tailed test with test statistic of 0.35. So to get p-values, we multiply by 2 to the normal CDF function on the calculator. And we get 0.7263 as the p-value, which is greater than our 0.05 significance. Depending on which method you use for hypothesis testing, p-value method or traditional method, listed here are the guidelines for rejecting the null hypothesis or failing to reject the null hypothesis. Doing an example, remember we figured the p-values out for these in example 4. We now can state whether to reject or fail to reject the null hypothesis. Example A, reject HO. Example B, fail to reject HO. Example C, reject HO. Example D, failed to reject HO. This page describes the proper wording when coming to a conclusion of a hypothesis test. Here are a few more examples on stating conclusions for hypothesis testing.